Well, welcome. My name is Steve Cross, and I am a retired, or what they call an emeritus professor from Oklahoma State University, where I was in the Civil and Environmental Engineering Department. And for about the last 8 to 10 years, I've also served as the technical director for the Asphalt Recycling and Reclaiming Association. So today, I want to give you kind of an overview or an introduction to full depth reclamation, or what we call FDR. So what we want to do in this presentation is give you a basic understanding of FDR construction, give you a little idea of where it should be used or where it works best. There are different categories of FDR, so we'll cover those. There are lots of different stabilizing agents that are used, so we'll talk about those and when and where they should be used and how they perform. And with some of these stabilizing agents, we put in additives as well. And so we'll talk about what they are and their performance benefits, and then give you just a general overview of some of the performance studies on full depth reclamation. So what is FDR? Well, full depth reclamation, it's a pavement rehabilitation technique in which the full flexible pavement section and a predetermined portion of the underlying materials are uniformly crushed, pulverized, and or blended. And what we do, put it back down and compact it, and this results in a base course. And if we had a stabilizing agent, it's a stabilized base course. Now, you may or may not have taken the class on cold-in-place recycling. So what's really the difference between FDR and CIR? Well, the equipment can be different, but cold-in-place recycling is limited to the flexible pavement or the asphalt pavement. And with FDR, we're going to grind up that entire pavement and get into the underlying materials. So that's the basic difference between the two. So a little bit of history. It's been around for a long time. And when it was first started, they would take the scarifying tines on the back of a motor patrol or use rippers attached to motor graders, and they would run it down the road and just rip up the pavement. That resulted in large chunks. So they would have to take hammer mills or grid rollers and run those over to bust the material up into smaller size so they could get it adequately compacted. And then sometime in about the 1950s, they developed these rotomixers. However, they were really developed to churn up aggregate base and subgrade. They really couldn't bust up asphalt pavement. So again, you would still have to rip up the asphalt pavement if you wanted to do FDR. So it still kind of hung around. But in the 1970s, they developed the large cold planing machines. And with that technology, they were able to produce these large self-propelled, high horsepower reclaimers that you see now. And these things are capable of pulverizing the mix, the asphalt pavement, and the underlying layers without having to rip it up into large chunks. It's not unusual for a reclaimer to be able to easily chew up 12 inches of material in a single pass. I've seen them go as deep as 17 inches in a single pass with the right material. 12 to 14 is much more common, though. So the development of those reclaimers has led to FDR as we know it today. So what kind of candidates? Well, FDR has been used on everything. So it's been used on interstate highways, been used on airports, down in the bottom picture, medium and low volume roads, been used on city streets, parking lots, etc. Can be used anywhere where you have an old, worn out pavement that needs to be economically reconstructed. As far as the distresses, since I'm going to take that asphalt pavement and I'm going to completely grind it up, I can handle just about any distress that I can reach. So I can handle all types of cracking that are in that asphalt pavement, from alligator cracking to block cracking to longitudinal to transverse crackage, slippage crackings, because I'm going to completely destroy that crack pattern. Potholes, rutting, shoving, pavement upheaval. I can handle pretty much any distress except one, and FDR alone will not fix a drainage issue. But that's no different than any other maintenance or rehabilitation technique. If you have a drainage issue, that needs to be fixed first. As far as the equipment, the self-propelled reclaimer that you see on the upper upper left for me. We're going to use one of those. We need a motor grader to spread this material out prior to compaction. We're going to need water trucks. Water is used for compaction. This is compacted like an aggregate base. It also can be used to help cure a cementitious stabilized layer. Because these are typically pretty thick layers, 8 to 12 to 14 inches in a single lift, we typically use pad foot rollers, although on some of the thinner ones we may not. But a pad foot roller, pneumatic roller, and a smooth drum roller. And then if we're going to stabilize it, if it's going to be bituminous or asphalt stabilized, we'll need a tanker truck for that. If we're going to put down cement, it's usually put down with a cement spreader truck. One of the things I want to point out, we're starting to see FDR performed with the single unit CIR train. And what this is a specialized, it's just a single unit CIR train. It's just a milling machine where they've modified the cutting housing to where it can mix the material. So the nice thing about this, using a single unit CIR train is I can mill up the entire lane width in one pass. Reclaimers are 8 foot wide, so it takes multiple passes to do a road. But with the CIR train, I can do this in one pass. So we've seen some people starting to look at this. But it usually takes a thinner section, and it's been done on stabilized sections. So typically, we don't see them going more than about 6 or 8 inches deep, especially if you're using an asphalt-based product. You have trouble getting that much material through the machine or getting that much recycling agent added. But South Carolina has done a 12-inch FDR section using a single unit train. So this is something that you might see in the future. But again, you want to concentrate not so much on the equipment that's being used, but how it's done. So types of FDR. We're going to break FDR down into several categories, and we'll go over each one of these in a little bit more detail. But there's simple pulverization. There's mechanical stabilization. We can do chemical stabilization, or we can do bituminous stabilization. So pulverization is by far the most economical FDR discipline. It's only done in a single pass, and what I do is I simply run my reclaimer down the road and I pulverize the asphalt layers in a predetermined amount of the underlying materials. Pulverize them, mix them all together, and then I compact them. Now, where would I want to use this? Well, there are lots of places where the pulverized material, you don't need to stabilize the base. With the quality of the material and the traffic and the surface course you're going to put on it is perfectly capable of carrying the anticipated loads, then there's no reason to do this. The only thing we add to this process with pulverization is water, and that's used for compaction. There are no stabilizing agents used. Then there's mechanical stabilization, and this is simply pulverization where I add additional material. So, and I'm also just going to turn just like with pulverization, I'm going to turn my pavement into an aggregate base. But there's lots of instances where I need to improve the cross slope or the profile or the grade or some widening where I don't want to sacrifice thickness, because again, you're usually coming into some roads that are in bad shape and you might want to do some improvements. So I can add imported aggregate, or I can bring in wrap, and I can mix this in and make it stronger base, or I can simply use it for grade improvements. We see a lot of times mechanical stabilization is used in combination with chemical or bituminous stabilization. If I need to make grade improvements or widening or something like that, and I also want a stronger base, then I can use mechanical stabilization with either chemical or bituminous stabilization. Chemical stabilization. This is by far the most common, and I'm going to use at least one of the following stabilizing agents. I'm going to use Portland cement, and it can be applied as dry or as a slurry. We like to use, cement's used very common because it works with a wide range of materials. But if I'm starting to get down and bringing up some clay or my contaminated base with a lot of clay, then I want to use a lime-based product. So they'll use hydrated lime or quicklime, and you can use that as a dry or slurry. In the past, we used to use type C fly ash, which was a self-cementing product. We don't see that used too much anymore. And then we can use kiln dust. You can use cement kiln dust or lime kiln dust. We see this used, recommend we only use this on low volume roads because the consistency of the kiln dust products are just not that good. They vary depending on things. You get up north, we see a lot of calcium chloride used. And then there are a whole host of proprietary chemical products that are out there that are changing all the time. There's too many to actually name. But cement is by far the most common, followed by lime. Like I said, we can put this down as dry or as a slurry. So dry stabilizers should be applied ahead of the reclaimer on top of the pre-pulverized material. So I'll do a pulverization pass. I'll shape and grade it a little bit, and then I'm going to spread my dry stabilizer. Now, one of the things about a reclaimer is it spins around in an upcutting mode, and it's not going to move material laterally. So whatever it picks up, it puts right back down in the same place. So when I spread my dry stabilizing agent, I have to spread it the full width of that drum width, and I have to put it down uniformly. So they have to be put down using a calibrated spreading unit. Otherwise, you won't get uniform mixing of the stabilizer. And slurry stabilizers can be dispersed ahead of the reclaimer on that second pass, or better yet, we're going to inject it into the reclaimer's cutting housing using the onboard material spray bar, and that will get you much better mixing. So it can be done either way. All right, with these cementitious, or some of them are pozzolanic additives, the strength is gained through the cementing of the material particles and the aggregates together in the reclaimed layer. So I'm going to turn these things into a solid. I'm going to bind them and cement them together. And so the strength gain is governed by the type of materials being stabilized, along with the type and the amount of stabilizer used. So the more wrap you put into the mix, the more asphalt that's ground in there tends to be a little lower the strength. The more aggregate base tends to be a little higher. But the biggest thing is the amount of cement. So the biggest problem we have with cement stabilization is too strong. We want low strength and we want a thick layer. A lot of specifications will tell you 200 to 400 psi of a 7-day unconfined compressive strength is what we're shooting for. And realize the most general run concrete is going to be 3,000 to 4,000 psi. So the problem is higher strengths can adversely affect the flexibility of the stabilized material and lead to fatigue cracking. But the biggest deal is the more cement that's in there, the more shrinkage cracking you're going to get. And then those shrinkage cracks will reflect through the asphalt overlay you put on top. So again, the key with cement stabilization is I want a low strength and I want a thicker section. For bituminous, we're going to use either foamed or emulsified asphalt. So the bituminous are asphalt emulsions, and they should be incorporated using a multipass process so you can get it mixed real well. So we'll pulverize it, grade it, shape it, then we'll come back and run it through again and inject the emulsified asphalt into the cutting chamber. It's a very cost-effective method for improving the strength of the material while reducing the effects of moisture on it. And it's more flexible than the other base course materials and chemical stabilizers. So it gives you superior fatigue resistance. It's not as prone to cracking. So, but it works over a narrower range of materials. The asphalt products don't like a lot of fines. So if your base course is relatively clean, you can use bituminous stabilization. If you start picking up more fines, you need to go to cement, and if you start getting clay, you probably want to go to lime. But the other nice thing about bituminous stuff, it works well in combination with other stabilizing additives. You can add other granular materials, or you can add a little cement or lime to give you a little better strength and a little better moisture resistance. So you will see those added occasionally. As far as what we use, emulsified asphalts, cationic emulsions are what's typically used because they break a little quicker, although we have used anionic and high flow emulsions in the past. One of the things you do need to do is you need to perform a mix design. You need to do that on cementitious as well. With mechanical and pulverization, there's no mix designs. We only run a proctor. But we want to run a mix design and make sure that our materials work well with our emulsion. And then there's two terms you'll hear sometimes. You'll talk about breaking and curing. So an asphalt emulsion starts to break when the water starts separating from the asphalt. An emulsified asphalt is a mix of water and asphalt, probably two-thirds asphalt, one-third water. And so when it starts to break, the water starts separating out and the asphalt droplets start going to the wrap in the aggregate. And then curing is as the water slowly leaves, the mix will slowly cure strength. So that's the development of the mechanical properties. This occurs after it's broken and it bonds together, and this can take quite some time. Depending on conditions, it can take a few weeks to a few months to gain its full strength. Bituminous stabilization. We're going to use foamed asphalt. This is quite popular with FDR because you need some fines in there. Typically requires somewhere between 5 to 20% fines or minus passing the number 200. And when you're bringing up that underlying materials, you almost always have a sufficient amount of fines. But foamed asphalt uses what we call neat or non-polymer modified asphalt. It can be a little difficult to foam polymer modified of asphalt. So how do we make it? I'm going to take hot asphalt, anywhere from 320 to 375 degrees Fahrenheit. I'll run it through a nozzle, and I'm going to inject a small amount of cold water, up to about 2% by the amount of the asphalt. That's going to immediately cause that water to turn to steam or to vaporize, and it's going to make tiny little bubbles of asphalt. So that thermal reaction greatly increases the surface area or the volume of the asphalt, reduces its viscosity, which allows you to mix it and get it compacted. So it works quite well with FDR. As far as the processes or the steps when I want to do an FDR project, well, the first thing I need to do is go out and analyze my existing materials. You shouldn't just blanket say, I'm going to do FDR with this stabilizing agent or that one. It should be based on the materials that you're going to be using. So then I'm going to analyze my existing materials. I'm going to begin the process with the pulverization process, and while I'm doing that, I want to monitor the depth of cut, and I want to monitor the gradation. By looking at the gradation, I can tell whether I'm getting adequate busting up of my particles. If I'm going to use stabilizer, I want to make sure I'm getting that properly mixed and compacted, or and spread to the right amount. I want to do an initial compaction with probably a sheep's foot or a pad foot. Then I'm going to shape my materials, final compaction, let it cure, and apply a wearing course. So we'll look at some of those processes. Biggest thing is I'm going to be digging into this pavement anywhere from 8 to 12 to 14 inches. So before I start this, I want to identify all active utilities within the recycling area. I want to lower them or mark them out so I can work around them. I need to identify all abandoned utilities. So, especially in an urban area, any old rail or streetcar lines, any raised roadway markings, or other castings. And I want to remove those prior to FDR. The one thing you do not want to do is to hit a manhole cover with that reclaimer, because that could be real exciting. Or if I hit any of these other utilities or chunks of iron, at best, I'll break the teeth off the drum. Worse, it could be very serious. Like any other project, I don't want vegetation and standing water from the edge of the pavement to get into this recycled mix. So I want to be sure I remove all that vegetation, sweep it clean. We're going to do this under traffic usually, so I want to set up my traffic control so it can be safely piloted or flagged around the work area. Again, that reclaimer is only about 8 foot wide, so there's generally plenty of room to work the traffic around it. If I have any drainage issues or any isolated base failures, it's nice to correct these before I get started. And any required grade corrections that cannot be addressed simply by the FDR, we want to get that done ahead of time as well, so I can get a nice uniform stabilized layer. All right, as far as the sequencing, we can do this in a single pass or we can do with a multiple pass. So the single pass is used when I'm doing simple pulverization with no stabilizers. If I have no major cross slope or profile grade corrections that are necessary. It also is used when I'm doing mechanical stabilization. Since I'm not mixing a stabilizing agent, a single pass generally mixes things well enough. But if I'm going to add a stabilizing agent, I want to be sure it's mixed in really well, and so I want that material pre-pulverized before I start. So with the multiple pass, I'll do a pre-pulverization pass. Then I'll come in and shape things up, because as you can see, the material fluffs and the tires will sink down a little bit, so I'll blade that back smooth. I might hit a real light rolling on it. And then I'm going to come back with the second pulverization pass, and during this pulverization pass, I'm going to inject my stabilizing agent. Then after I've done that, I'll do compaction, fine grading, and then I'm going to cure that surface. I'll either add a fog seal or prime coat as needed, and then eventually I'll apply the specified wearing surface. This is going to go down at high voids. It's going to need some type of a wearing surface to protect it from moisture damage. Compaction. Compaction is critical, especially with mechanical, pulverization, and bituminous. It's not quite as critical with cementitious because I'm going to cement stuff together, but I still want everything adequately compacted. And because of the thicker depths, I typically am going to use a pad foot compactor, which will allow me to compact this material from the bottom layer up. So after I hit it and it walks out with a pad foot compactor, I'll grade the road with a motor grader to get it close to grade, and then I might hit it with a rubber tire roller, a heavy one, 22 to 25 to 30 tons, and then I might use a single drum or a double drum vibratory roller to compact it. I'll use either the rubber tire or the double vibratory, and then my final rolling is usually done with a single or double drum static roller. But compaction is critical. With bituminous, we oftentimes control it with modified proctor. With cementitious, it usually uses standard proctor. As far as quality control checks, we always want to check the depth of pulverization and check our mixing. We want to check the gradation of the pulverized material. This is generally just checking the maximum size. If I'm putting down a stabilizing agent or additives, I want to check the application rate. If they're being spread dry, I'll usually use something like a canvas patch test where I'll lay the material down, pick up the canvas, weigh it, and make sure I'm getting the right amount. I also want to do a yield check with any tanker loads of material, figure out how far they should spread, and check and see how they did. I always want to check compaction, and then we want to check our final grading alignment after we get everything compacted. Weather limitations. I don't want to do this when the pavement's frozen or when I have freezing temperatures anticipated within about 7 days at the end of the FDR placement. I want it to adequately cure. As far as minimum temperatures, with cement you can go, or the chemical you can go a little colder, so a lot of times we'll see 35 degrees and rising. With the bituminous, it's typically 40 to 45 degrees and rising. And FDR should not be performed in moderate to heavy rain. Realize we are adding moisture to this mix with compaction. So if we're getting light rain, and as long as we're not spreading a dry chemical agent, a light rain's not particularly going to hurt us. But we want to watch out for heavy downpours. As far as preparations for the wearing surface, this mix needs to cure out. So for chemical stabilization, I want to put I want to moist cure it continually until I can get a curing membrane on it. And we want to leave that curing membrane on it for several days until it's gained its strength before I put the final wearing surface on it. With the chemical one too, I also want to be careful to not let heavy loads go down on there because I can break this material up before it's gained adequate strength. Bituminous ones, we can usually put traffic on it at the end of the day. Before I overlay it, I'm probably going to put down a tack coat, and then I can put a wearing surface on it. And we've seen everything imaginable put on here, from chip seals, slurry to micro cape seals. We've seen cold mixes put down over it, hot mix, and even in a few instances they put concrete pavement down over it. But whatever is structurally required for your pavement section, but it can handle almost anything. As far as performance, again, there's plenty of information in the literature documenting the performance. It's been used on all traffic levels of roadways and airports. A couple we'll talk about. Virginia DOT used FDR on I-81 and I-64, and then they put down some sections at the NCAT test track. MnRoad has some sections up there for cold weather. South Carolina's probably done as much FDR with cement as anybody, and there's lots of other states that have experience with this as well. So on I-81, the left lane of a truck lane, they came in and put 12 inches of FDR, 8 inches of CCPR, and 4 inches of new asphalt on it. It's been been down for more than 9 years, but the data I had said after 9 years, it had close to 20 million easels, which is very high traffic, and they've experienced no rutting or no cracking, and the IRI was less than 50 inches per mile, which is in the very good category. So it's been performing quite well. Then Virginia took those same sections they put down on I-81 and took them down to the NCAT test track. So S12 is the FDR section, 8 inches of FDR, 5 inches of CCPR. It went through 3 full cycles, so actually 9 years and close to 30 million easels, and there's been absolutely no distress on S12. In fact, they think this might be what they call a perpetual pavement, in that that base is so sound that you get such little strain in the bottom of the asphalt layers that they should never fail. So they are continuing to monitor this one section to see how long it will last. But it's been working quite well. And then I-64 Williamsburg, this was a project that we're going to do some reconstruction and widening of some lanes. And the I-81 worked so well that VTRC gave them an alternative proposal. The original design was an 8-inch of cement-treated aggregate, 4 inches of asphalt, and 4 inches of SMA at an estimated cost of $71 a square yard. The counter proposal was, let's come in and let's just do FDR. So they did 12 inches of FDR. They imported a little bit of material in that, so it was kind of a mechanical with stabilized FDR. And then they put 6 inches of cold central plant on top of that, and then 4 inches of SMA. And that's pretty close to what's being done. So they had the same structural value, but 36% lower cost. So it's estimated at $71 per square yard to $45 per square yard. So one of the nice things about FDR is it builds structure into your pavement if you stabilize it, and it can be very cost effective. The last one we want to cover is up in MnRoad, and this is this is a cold weather application. And on the actual MnRoad test section, which is I-94, there are 3 FDR sections with emulsified asphalt that have been down quite some time. 2 of them have performed excellent. The third one, I think, had some drainage issues. But they came back with 70th Street back in 2019, and we're going to do several different test sections. So they put down some CIR test sections, some CCPR test sections, and FDR sections. So the existing road was a 4-inch asphalt road with 6-inch granular base and a clay subgrade, which was in very poor condition, and FDR was probably what it needed. So they put down 2 7-inch thick FDR sections, and they put a 1-inch asphalt overlay or thin layer on top of it. One of the sections had foamed asphalt, and it had 1% cement with it. The other one was an emulsified asphalt on its own. Like I said, these were put down in the summer of 2019. They've been performing quite well. And the traffic that's estimated on it, it would be somewhere between low volume to kind of an intermediate volume traffic. But again, so far been performing quite well. It'll be interesting to see how these hold up. So, in summary, the nice thing about FDR, it's going to eliminate most pavement distresses you have. You're going to use this at a pavement that's toward the end of its life. You're going to take a deficient pavement structure, whether it was never properly designed or simply had way more traffic than it had ever intended, and I'm going to turn it into a new homogeneous section with increased structural capacity. I'm going to turn it into a stabilized base. As far as cost savings, you can see anywhere from 25 to 50+% cost savings compared to other rehabilitation methods. If you think about it, I'm going to take that existing road. I already own all those materials. I'm going to grind it up, add a stabilizing agent, and recompact it. So one of the other things that makes it quite sustainable is I'm reusing 100% of the existing materials. But if you think about it, if I'm going to reconstruct it, I've got to haul all that material off, and then I've got to turn around and haul all new material in. So FDR greatly reduces trucking and conserves non-renewable resources. And I can return it to traffic the same day, light traffic. So very cost-effective, very sustainable, well-performing process. So with that, that concludes my introduction to FDR. I appreciate your time and attention.